everyone, thanks so much for clicking onto the video. Today we're going to have these two learning objectives, and the first is to understand experiments to measure enthalpy changes. So we're going to be looking at the Q equals mc delta T equation, and then we're also going to be evaluating sources of error and assumptions made in the experiments. So we're going to be looking at substances mixed in insulated containers, enthalpy of combustion measured by burning alcohols, and we're also going to learn that enthalpy change cannot be measured directly. The next learning objective will be to be able to calculate enthalpy changes in kilojoules per mole from given experimental results. So now we're going to look at an equation that will eventually help us find the enthalpy change of a reaction. So this equation actually helps us find the heat energy difference, so the heat energy given in or the heat energy given out. So Q represents the heat energy taken in by the reaction if it's endothermic, or given out, and that's if it's exothermic. And this is normally measured in joules, and this is a unit of energy. M stands for the mass of the solid which is being heated, and this is always measured in grams. Next we have C, and this is something we call the specific heat capacity. And what that basically means is the amount of energy, the amount of heat energy needed to raise the temperature of 1 gram by 1 kilogram, by 1 degree. So the amount of heat energy needed to raise 1 kilogram of something by 1 degree Celsius or 1 Kelvin. These two are equivalent. And this is measured in joules per gram per Kelvin. And then we have this delta T. T stands for temperature, and the delta just means the change. So it's the change in temperature between before it was heated and after it was heated. So this is the change in the temperature. And this is always measured in Kelvin. And then after we found the energy which has the heat energy which has been released or taken in, we can then find this enthalpy change. And enthalpy change is always per mole, and it's always measured in kilojoules per mole. And looking at this equation, how to find it, we divide the energy change which has occurred. So this again is the heat energy given out or taken in. We divide that by the number of moles which are reacting, and that's how we get kilojoules per mole. But if you remember, this heat energy here is actually measured in joules. So that means that we need to convert this into kilojoules before dividing by the number of moles to get the enthalpy change, otherwise it will go wrong. So it's really important to remember all the units for these two equations, because when you're working them, when you're using them in questions, they'll try to trick you by using different units. So just make sure that you know what all the units are. Now we're going to look at an example of how to calculate the enthalpy change. So in an experiment, 0.600 grams of propane was completely burned in air. The heat evolved raised the temperature of 100 grams of water by 64.9 degrees Celsius. Use this data to calculate the enthalpy change of combustion of propane. It will always give you the specific heat capacity of whatever you're heating up, so you're not expected to know that. Now, Because it's completely burned in air, we definitely know that we can use the enthalpy change of combustion, because the definition of enthalpy change of combustion is energy change when, I'm just going to put down some keywords. So energy change when 1 mole is completely combusted with everything in standard conditions and states. So we know we can definitely use the enthalpy change of combustion, but in this example, that doesn't really matter because they give it to you anyway. So the first thing to do is to remember the equation, which is Q equals mc delta T. And now you need to remember all the units. So I quickly like to jot down in the corner what all the units are. So this one's joules, this one's gram, this one will be Kelvin. And if you forget that, it's very useful to look at their specific heat capacity, because it's joules per gram per Kelvin. So if you rearrange this formula to get the C as the subject, you get C equals Q over M delta T. So you must have joules over gram over Kelvin. And that's what that corresponds to this. So if you ever forget the units, sometimes it's very useful to look at the specific heat capacity if they've given it to you with the units. Okay, so we're going to work with this equation here. And we need to remember that M is 100. So M equals 100. And then C we know is 4.18. And then delta T is 64.9 degrees because the heat involved raised the temperature. So that's the difference, is 64.9. And it doesn't matter, but it doesn't matter if it's in degrees Celsius, because a 64.9 degrees Celsius rise is the same as a 64.9 Kelvin rise. So we get Q equals 100 times 4.18 times 64.9. And that comes out to be 27182.2. And then we round it to 27130 joules, which equals 27.13 kilojoules. Now I've converted it to kilojoules because it helps us with the next step. And now we move on to the next equation, which is finding the enthalpy change. So we have delta H equals Q over moles. And we always have to remember that delta H is measured in kilojoules per mole. And that's why I've converted it here. So now we need to find the moles. And this moles corresponds to the moles of propane. So moles of C3H8 is the mass over the molar mass over MR, which equals the mass, which is 0.600. And then you divide that by the MR. So we know that the AR of carbon is 12, so we've got 3 of them. So we've got 12 times 3, and then we plus 8 because each hydrogen is 1. So that's 0.600 over 44. And that comes out to be 0.01364 moles. And now we can put that into our equation. So delta H equals 27.13 divided by 0.01364 moles. But because it's a combustion reaction, we know that energy is being released. We also know this because the heat is raised. So the heat of the surroundings is raised, which implies that it's an exothermic reaction. And because it's an exothermic reaction, we need to label this heat energy change as a negative. because the actual thing has lost energy, but it's just heated up the surroundings. So that's something really important to remember, is the minus sign. And it's the opposite for endothermic reactions. So for endothermic reactions, it'd be a plus sign. So now we've added a minus sign here, and there needs to be a minus here. And this turns out to be minus 1,990 kilojoules per mole. And I've rounded this to 3 significant figures because if we look back at the question, everything looks like it's in 3 significant figures. So we've got the 100 grams of water and the 64.9 degrees and the 4.18 for the specific heat capacity. So everything looks like it's in 3 significant figures, so I've rounded it to 3 significant figures. And it's very important to remember this minus because marks can be deducted if you forget the minus or the plus. So now we're going to look at some experiments that we can perform to help us find the enthalpy change. And so the first one I'm going to start off with is this simple colorimeter. And in a polystyrene cup, we can add in 2 solutions, so maybe an acid and an alkali. And when we mix them together, it should be exothermic, so heat should be given out. So we use the thermometer to measure the temperature before, and then we plot a graph. So we set a specific number of time between each, like time intervals between where we take the temperature, and we get a graph kind of like this. So this is an exothermic graph because initially the temperature increases because the heat's given out. So this is the initial temperature of the solution, and then it rises very, very rapidly, and then it starts to decrease again. So the whole point of these graphs is so that we can find out this delta T, so the change in temperature. So we extrapolate it back because these ones are inaccurate because the temperature is still rising. So we want it where the temperature is at its highest. So we extrapolate this graph back to find this change in temperature at the beginning, and this is what we use in the equation Q equals mc delta T. So here is where we use this value. And then if we've got an endothermic reaction, it'll be the opposite of this. So the points will start off here, and then they'll start to decrease, and then you'll get some here, and then they'll start to increase to around room temperature again. So here we extrapolate the graph this way to find out this delta T. And then we use that in this equation. So this is an endothermic graph. And the thing with extrapolation is that it's not entirely accurate because we actually don't have any data points over here. We've just kind of guessed where they would lie. So there is some inaccuracy. And this second experiment is with a copper calorimeter. So this is slightly more inaccurate because we're using a polystyrene cup, even though it is well insulated. So less of the heat is kind of going out, and all of it we can account for in here. But this is probably a little tiny bit more accurate, but still there are heat losses to the surroundings, and also the copper does absorb some of the heat itself, so not all the heat is going to raise the temperature of the water. So we've got lots of insulation, we've got the draft shield, the insulating card, and what we do here is we burn an alcohol. So we weigh the alcohol before, and then we also measure the temperature of the water before, and then we burn the alcohol. So we set it alight, and then we continue burning it, and then we burn it to something that we've already decided. So we could decide that, oh, we're going to heat up the water 30 degrees maybe. So that's when we would stop heating up the alcohol, the fuel, and then we would reweigh the fuel, and then we would take the final temperature, which should be what you've already decided, and then you would use this Q equals MC delta T again, and then the delta H, the enthalpy change, equals Q over moles. And this moles here would be the moles of the fuel burnt, and this M here would be the mass of the water which has been heated. One thing to note is that enthalpy change cannot be measured directly, so we always have to measure the temperature and then use this equation and then this equation to measure to find the enthalpy change. Now we're going to discuss some sources of error. So there's actually quite a lot of error when we do these kind of colorimetry experiments, because lots of the heat is actually lost. So the delta T that we calculate is actually quite inaccurate. So the first error is heat loss to the surroundings. So basically the heat hasn't all gone to the water to heat the water up, it's gone into the surroundings as well. The second is an inaccurate thermometer. So if it's inaccurate, then it's very unlikely to be measuring the actual temperature of the water at specific times. So it might be like 0.2 degrees out, which can be quite a lot. It can like throw your data. The third is the specific heat capacity of water is exceptionally high, and this is due to the energy required to break down hydrogen bonding in water. So when you heat the water, some of the absorbed heat goes into increasing the vibration of the hydrogen bonds to weaken them and to try and break them, rather than being absorbed directly to increase the kinetic energy of the water molecules and like actually heating up the water. Number 4 is when salts are dissolved in water, the hydrogen bonding is actually disrupted as the water molecules congregate and they gather around the ions in the process, and this is called hydration. And this has the effect of actually lowering the specific heat capacity of water. And if we use a more concentrated salt solution, then the heat capacity actually lowers even further. So our specific heat capacity of water that we're using, which is normally 4.18, it might actually be much higher than what it actually is. So number 5 is heat loss to the container. So the container is normally copper, so it's made out of metal, so it'll conduct the heat energy. So not all the heat will be used to heat up the water. And this is the same with the thermometer. So you have mercury or glass thermometers, and both of those materials tend to absorb heat. And number 7 is unreacted substances. So when we have things which haven't gone to complete reaction, then not all the heat will have been given out or taken in. So that can also throw your results. So now we're going to look at a question. Feel free to pause the video and try it out for yourself first. So 500 centimeters cubed of 1 mole per decimeters cubed of hydrochloric acid was added to 500 centimeters cubed of 1 mole per decimeter cubed of sodium hydroxide. The temperature rose by 6.8 degrees Celsius. Calculate the enthalpy of neutralization for this reaction. Assume the density of the solution is 1 gram per centimeters cubed and that the specific heat capacity of the solution is 4.18. So first what I would do is to calculate the moles of hydrochloric acid and sodium hydroxide to see what actually reacts. So the moles of hydrochloric acid equals the mass over the molar mass. So actually for this one we use concentration times volume because we're not given the mass. So we have concentration times volume, but these have to have the same units. So we're going to use decimeters cubed. So we need to convert this to decimeters cubed. And the way we do that is divide it by 1,000 or times 10 by -3. And then we times it by the 1 mole per decimeters cubed. And this gives us 500 times 10 to the minus 3. And then we do the same for the sodium hydroxide. And this is actually exactly the same. 500 times 10 to the minus 3. And then the next step is to look at the equation. So when we mix sodium hydroxide and hydrochloric acid together, we form salt and water because this is an acid and alkali reaction. So we form the salt NaCl, sodium chloride, plus water. And this is already balanced, so this is the equation. And then we look at the ratio of sodium hydroxide to hydrochloric acid reacting. And as we can see, it's just a 1-to-1 ratio. So it's 1-to-1 ratio, and that's for the moles. So if we looked at hydrochloric acid and we've got 500 times 10 to the minus 3, then that means that 500 times 10 to the minus 3 moles of hydrochloric acid would react with 500 times 10 to the minus 3 moles of sodium hydroxide. And we have that here. So that tells us that none of the reagents are in excess, so both of them react until they've both finished reacting, there's nothing left. So that actually doesn't make a difference. So we know that 500 times 10 to the minus 3 moles is what's been reacted. So now we use our Q equals mc delta T equation. And then we need to remember the units. So this is grams. This is already given to us, and this is either degrees Celsius or Kelvin, it doesn't matter. And this will come out in joules. So now we just plug in the values. So the mass here is the mass of the solution. So the solution would just be 500 centimeters cubed plus another 500 centimeters cubed. So that would be 1,000 grams. And then you times it by the specific heat capacity, which is 4.18. And also a centimeters cubed is equivalent to a gram. And then you times that by the 6.8 degrees rise. So for that, you should get 28,420 joules, which is equivalent to 28.42 kilojoules. So that's the heat energy that's been given out. And now to find the enthalpy of neutralization, which is just the enthalpy change, is we use delta H equals Q over moles. So here for the moles, it actually doesn't matter which moles we use because we actually use the same amount of both. So we do 28.42 divided by 500 times 10 to the minus 3. And that gives us minus 568.4, because the minus here signifies that it's an exothermic reaction, so we definitely need to remember that. And we round this to minus 568 kilojoules per mole. And the rounding is also really important because you can get marks deducted from not rounding correctly. So in the questions, we can see that lots of these figures are to 3 significant figures. So that's what gives us a clue to what to round this to. So we've also rounded this to 3 significant figures. Hi everyone, thanks so much for joining me for this video. We're going to look at some harder questions for the topic of calorimetry now. So the first question says, the enthalpy of combustion of propan-1-ol is minus 2020 kilojoules per mole. 0.6 grams of propan-1-ol is burnt and used to heat 200 grams of water in a calorimeter. The starting temperature of water is 20.3 degrees and the specific heat capacity of water is 4.18. How much heat is released when 0.6 grams of propan-1-ol is burnt? Now, the first thing we do is we write out the two equations we know. So we know Q equals mc delta T, and we also know delta H equals Q over moles. And now we have a look at what information we have. So here we have delta H, and this is the mass of the propan-1-ol. This is our M, because you have to remember that for this equation, this always talks about the water or whatever's being heated. So the M here will be this 200 grams and not the 0.6 grams of propan-1-ol. The starting temperature is 20.3 degrees. And we've also got C here, which is the specific heat capacity. So from this, we can tell that we can't use this straight away because what we're trying to find is the delta T. And so we use this equation first. And we have the delta H, and we can find the moles by using the mass here and dividing it by the MR. So if we rearranged this formula to get Q as the subject, then we can hopefully use it in this equation, which has been, if we rearrange it to find delta T, then we'll be able to find it. So Q equals delta H times by moles. Delta H we know is minus 2020, and then you times by the moles, which is mass over the MR. So we have 0.600, and then the MR, which is, we've got 1, 2, 3 carbons, so that'll be 3 times 12, and then you plus 3 hydrogens, 2 hydrogens, 2 hydrogens, and another hydrogen, so that's plus 8, and then we also plus the oxygen, which is 16, and this gives us a total of minus 20.2 kilojoules. And then we remember that in this equation, we have to have Q in joules. So we have to convert this back into joules. So that's minus 20,200 joules. And then we rearrange this formula. So we get delta T equals Q over mc. And then plug in all the values we know. So we have the Q. It doesn't really matter now to include the negative because that's just telling us that heat was lost to heat up the surroundings. So we can ignore that. So we get the 20,200. And then you divide by, this is now the mass of the water, so 200. And then you times it by 4.18 because that's the specific heat capacity of water. And then you get 24.1 degrees Celsius. So this is the change in temperature because that's what delta T means. And so in order to find the theoretical temperature of the water at the end of the experiment, we then add this value onto 20.3 because it's exothermic, so the temperature is increased. So this is the answer for A. And then for B, we do 20.3, which is the starting temperature of the water. And then you add on the 24.1 because it's exothermic. And then you get 44.5 degrees Celsius. And one thing to note here is that when we calculated this, it came out as a decimal. So it came out as 24 point and then a few decimal places. We rounded it to 24.1 for A because everything else is in 3 significant figures. So this should be in 3 significant figures. But then when we use it for other calculations, we need to use the actual figure. So we don't round it to 24.1, it'll be a decimal again. So that's how we get 44.5 degrees after rounding. And that's also to 3 significant figures. And then for C, is the final temperature likely to be higher or lower than this theoretical answer? The answer is that it will likely be lower. And this is because lots of the heat will actually be lost to the air or also to the container that it was in. So heat loss makes the experiment less accurate. So it goes to the air, or you could say it goes to the container, but basically it just doesn't heat up the water, because it's not only just heating up the water, it's heating up other stuff as well. So that means that the actual temperature of the water at the end won't be as high as 44.5 degrees. So this second question is a bit more involved, but feel free to pause the video and to try it first. So 50 centimeters cubed of 0.1 molar of silver nitrate solution was put in a colorimeter and 0.2 grams of zinc powder was added. The temperature of the solution rose by 4.3 degrees. First work out which reagent was in excess and then calculate the enthalpy change for the reaction per mole of zinc. So assume that the density of the solution is 1 gram per centimeters cubed and that the specific heat capacity of the solution is 4.18. And we ignore the heat capacity of the metals just for simplicity. So first what I do is work out how many moles of silver nitrate solution and how many moles of zinc we have. So the moles of silver nitrate, now they only give concentration and volume, so we can't use the mass over MR formula. We have to use concentration times volume. And it's normally volume in dm cubed and concentration in moles per dm cubed. So we're going to convert this 50 centimeters cubed to decimeters cubed. And the way we do that is divide it by 1,000 or times 10 to the minus 3. And then we times it by the 0.1. And this gives us 5 times 10 to the minus 3 moles. And then I'm going to work out the moles of zinc. And now we can use the mass over MR because we're only given the mass. So we have 0.2 over the MR of zinc is 65.4. And that gives us 3.06 times 10 to the minus 3 moles. And now we look at the equation and we look at the ratio. So the equation tells us that 2 moles of silver nitrate react with 1 mole of zinc. So if we first look at the silver nitrate, that means that if we have 5 times 10 to the minus 3, then that should react with half the amount of this number of moles of zinc, because it's a 2-to-1 ratio. So then it would react with 2.5 times 10 to the minus 3 of zinc. And if we looked at it the other way around, so if we start off with the zinc, if we have 3.06 times 10 to the minus 3 of zinc, then that would react with double that amount. So that would react with 6.12 times 10 to the minus 3 of the silver nitrate. So now we've written the ratios out, we can see that if we go with this method, we don't have enough of the silver nitrate because we've only got 5 times 10 to the minus 3, so we can't do this. So this must be happening. And so this also tells us that the silver nitrate, that the zinc is in excess, because only 2.5 times 10 to the minus 3 moles of it reacts, but we've got 3.06 times 10 to the minus 3, so we've got more than what there is to react with silver nitrate, so there's some left at the end. So now we write out the equation that we know, so Q equals mc delta T, and plug in the numbers. So mass here would be the mass of the solution that's been heated. So we've got 50 centimeters cubed of it, and that's equivalent to 50 grams. And then we multiply it by the specific heat capacity of the solution, which is 4.18. And then multiply it by the change in temperature. And it says here that the temperature of the solution rose by 4.3 degrees. And this comes to a certain amount of joules, which I've converted to kilojoules. So it's 0.8987 kilojoules. And now we use the delta H formula. So we've got delta H over Q over moles. And here, the question asks for per mole of zinc that reacts. So this is going to be mole of zinc that reacts. So we'll have 0.8987 over the moles of zinc which have reacted, which is the 2.5 times 10 to the minus 3. And then that comes to minus 359.48 kilojoules per mole. And now we look back at the question and have a look to see how many decimal places or significant figures they've rounded everything to. And it looks like they've all got 2 significant figures. So then we round this to minus 360 kilojoules per mole. And I've added in the minus here because it's an exothermic reaction. Technically, you can add the minus here, but so that's better if you think you'll forget it. But adding at the end is fine as well, as long as it's in the final answer.